Hello everyone and welcome to this new LATI webinar. The topic of the day is quite interesting, maybe a bit difficult, but for sure quite promising a strategy for the applications of the days to come. We will talk about electromagnetic radiations, where do they come from, how to protect from them, solutions and materials. The agenda is quite crowded actually, but we will try to be as clear as possible. First of all, we will need to introduce the electromagnetic phenomena. So we have to understand where do the electromagnetic phenomena come from and what is their effect on plastics. Then we will have to introduce the topic of electromagnetic compliancy and shielding. The second part of the webinar will be dedicated to share with you the numbers, the shielding efficiency measurements that we got from the Aachen University on some of our materials, some of them already existing, some of them brand new. And then we will draw our conclusions, of course. Before starting the webinar, I have to highlight the fact that the physics of electromagnetic radiations and electromagnetic fields are quite complicated. In order to make everything clearer and understandable, I had to introduce some very gross simplification. I did my best trying to keep everything as correct as possible, but I beg pardon to the most expert of you in case something that you see is not perfectly accurate, at least from a formal point of view. Anyhow, let's jump into the topic. At the end of the webinar, I will be happy to answer all your questions if you may have one. Please follow us on LinkedIn and please follow our previous webinars we already released in year 2021, 22, 23. You can find all of them on our YouTube channel. So let's understand what is electromagnetic radiation and how plastics interact with electromagnetic fields. First of all, we have to understand what is an electromagnetic field. Each time we have static charge, we have electric charges, we can define the existence of an electric field, which is the force field generated by the presence of charges. What happens if electric field is applied to a conductor, to a conductive material? In this case, the electric field will generate an electric current. How do we, let me say, how do we understand better what is an electric field? The electric field is measured in volts, so it's actually voltage. If you want to understand, to have the feeling of what is an electric field, each time you have voltage, you are dealing with an electric field. That's the reason why applying a voltage to a conductor, you can actually create current. I know this is not accurate, but to let everybody understand how it works. Whenever you have current, electric current, you are dealing not only with an electric field, but also with a magnetic field, which is actually created by moving charges, being them electric, alternate current, or direct current. What happens when these electric fields meet plastics? First of all, we have to understand that electromagnetic fields are not static. The electromagnetic radiation moves through space in a wave, which is composed by the electric field and the magnetic field. You can see the layout right here. They are both perpendicular one each other, and they are perpendicular to versus the propagation direction. An electromagnetic radiation has its own intensity, which is actually the strength of the field in itself, and frequency, that is how many times this sinus wave alternates. Let's suppose that this field meets a polymer. What happens? As you know, plastics are electrical insulators, so they do not conduct electric current. So actually there is no flow of electric current through plastics. How do we measure this? By measuring the resistance of the plastic part. And through resistance, dealing with the geometric size, length, and section of the conductor, we can derive resistivity, which is the material property. Resistivity for plastics is extremely high because they are insulators. But I would like to focus your attention on the fact that, just to give you an idea, For polyamides, this resistivity is strongly affected by the presence of moisture. So resistivity is a property of the material, but it should not be considered as a constant, as it can vary quite a lot. This first way of the electromagnetic field to couple with plastics is called conductive coupling. So the first thing that can happen is to try to have an electric current. The plastic material will resist, and this is what we measure. That is resistivity. Is it all? No, it isn't, because in the macromolecule you can have some of the chemical bonds, which are actually electric bonds, that can be not perfectly balanced. You can have the so-called dipole. In the macromolecule, you have plenty of dipoles in the macromolecule of polar plastics, like some polyamides, just to give an idea. What happens when electric fields meet these dipoles? You have strong orientation of these dipoles. So they move in the direction of the electric field in order to be compliant with the strength and direction of the electric field. And this leads to the buildup of charges on the surface of the plastic part. The phenomenon is known as polarization. It does not occur only in plastic, of course. You can describe it introducing another vector, another tensorial space, which is called polarization. And we can suppose that polarization, letter P, is proportional to the electric field via the susceptivity, electric susceptivity of the material. If we combine the electric field E with the polarization P, we can define, let me say, an overall electric field, which is called electric displacement field, that can be supposed proportional to the generating electric field E via this magnitude epsilon. Epsilon can be somehow describing the way the material is interacting with the electric field. And for this reason, we introduce the electric permittivity, which is epsilon with R, which is also called the dielectric constant of the material. The electric constant is not the most correct way to call it, but okay, we generally accept it as a dielectric constant of the material. The dielectric constant of the material is actually describing the way the material is capable of transmitting the electric field. And this is a property of the material which should be given by the compound, by the plastic supplier, as it is extremely important for many electric and electronic applications in the field of plastic applications. For polymers, this is a relatively low value, ranging from 2 to 7 normally. And for polar polymers, we can see that it diminishes as frequency increases. Another property which is also quite a lot sought after when we have to describe the electrical behavior of plastics is the so-called dielectric strength, which is describing the strength of the electric field that is required in order to create a discharge in the material. This is just an overview to give you an idea of the numbers when it comes to electric permittivity and the electric strength of 3 plastics, high density polyethylene, polyester, and polycarbonate, just to give you an idea. Is it all? No, not yet. So we have seen resistivity, we have seen the electric constant, we have seen the electric strength, what are the meanings of these properties, but we have another one to find out. The orientation of the dipoles in polarization is not immediate. This means that we actually have some delay, and this delay can be described dividing the electric constant into a real part and a complex part. The complex part, the ratio between the two, is called loss factor, and it is identified as tangent delta. For sure, you have already heard it. It's a quite required property of the material, especially when it comes to application where you have to deal with the capacitive effect of plastics. Here you see how this complex part, this loss factor, actually behaves. It's often is due to the to the side branches of polymers. Anyhow, this way of the electric field to couple with plastics is somehow recalling the effect of a capacitor, and for this reason it is called capacitive coupling, and this is due exactly to the different voltage of the electric field existing between two conductors. As I told at the beginning of this presentation, whenever you have an electric field and moving charges, you also have a magnetic field. What are the effects of magnetic fields on polymers? You can somehow describe the magnetic field, the effects of magnetic field as we have done for the electric field. So instead of polarization, we will talk about magnetization of the material. We can somehow create the same way a magnetic susceptivity, and we can of course create a property of the material which is somehow similar to the dielectric constant, which is called the magnetic permeability of the material, which is actually describing how much the material is capable of conveying the lines of the magnetic field in itself. We are lucky from one point of view because plastics have no magnetic behavior. They are called diamagnetic, so their magnetic permeability is really very low, close to zero. This kind of coupling is called inductive coupling. So we have seen conductive, capacitive, and inductive coupling. But it is not all yet, because we also have to deal with the radiative effect of the electromagnetic field. So to resume what we have seen right now, plastics behave as electrical insulator. There is no current flow. If we want to describe it, the behavior, we have to recall the resistivity of the material. So resistivity will be one of the properties you need to find on your technical data sheet. Plastic can give static charge buildup. They behave as capacitors. So you have the measurement of this dielectric constant and the loss factor tangent delta. And then plastics have no magnetization. So normally the magnetic permeability of plastics is not an interesting property, at least for an entry-level application. Now, what is an electromagnetic radiation? The electromagnetic radiation is the propagation of the electromagnetic field in space. Today we have plenty of applications which are actually using and applying correctly this propagation in the space of the energy of the magnetic field. Some examples: radio frequency RFID. How does it work? You have a source which actually propagates information via electromagnetic wave, and this is captured by an antenna and transformed into current and tension, which are actually charging up the receiver and providing information. This is RFID. We have some RFID like this one shown here, working between 125 kilohertz and 8 gigahertz. And then we have a new field of communication using the magnetic wave, which is the near field communication, as the one we use in our cell phones for payments, credit cards, post payments, and so on. These are the electromagnetic waves that we want to create to use them. So we can somehow create groups and put electromagnetic waves in these groups. Electromagnetic waves can be divided then into the intentional waves, radio, radar, payments, and so on. Then we have applications which are actually producing electromagnetic waves, but it is not their goal. We are dealing with irradiated collateral electromagnetic waves, like natural phenomena, electric lines, computer motors, inverters, converters, power supplies, and so on. And then we have electromagnetic waves which are created and captured by the same device, the so-called intrasystem waves. What are the effects of these not desired electromagnetic waves once they get into our application. We know them very well. Electromagnetic interference, called EMIs, can be extremely harmful in both cases, as whether they are in the input stage or the output stage. They will transform the shape of the signal. They will create power surge. They will lead to noise disturbances, to data loss or distortion. They can actually also create hardware issues and damage equipment. And last but not least, this is still a very discussed topic, but there is also some interest in the effects of electromagnetic waves on human health, especially when it comes to low frequency, high intensity magnetic waves, magnetic fields, as the ones that you find close to high power high tension power lines. Just to give you an idea, this is a car, and this is the number of devices that we can find on our cars. You can see how many of them and how many different frequencies these are actually using. So you can easily imagine how high is the risk of having a proper interference between all these devices. When it comes to electric vehicles, so the most modern one, please remember that on an electric vehicle, we are dealing with high voltages and high current. So normally, the electromagnetic waves that are created into an electric car can be extremely powerful and extremely harmful. Just to give you an idea, let's insulate one of the devices that we can find on an electric car. Let's talk about a power converter, which is used to transform AC to DC to charge the batteries. What is the frequency that is released by a power converter? It is depending on the kind of transistors used in the electronics, but you can find from 20 kilohertz to 4 megahertz. These electronics anyhow release harmonics, high frequency harmonics, especially 2.5 gigahertz, and these harmonics can be extremely harmful to Bluetooth and data management device. They can also bring to actual mechanical failure on the car in itself. How do we protect our application from these harmonics and not desirable interference? We have two ways. We can try to filter them out along the way. So in our electric layout, we put some capacitors, some P filters, and so on, but this means adding weight and adding safety issues to our car, to our device. Or we can try to shield them and to shield our application from them. So we have to take care of the efficiency of these shields. Now, we have seen the problem. We have seen what is an electric field, electromagnetic field. We have seen how many electromagnetic fields can create interference in our applications. Now, let's introduce the concept of electromagnetic compatibility. What does electromagnetic compatibility means? We have a good magnetical compatibility of an electrical equipment each time our equipment can work safely and correctly in an electromagnetic environment without being altered by emitted or without being affected by incoming radiation. So the device is compliant, electromagnetic compliant, as long as it does not interfere with other device or is not affected by incoming device. In order to guarantee a good electromagnetic compatibility, we have to deal with the topic of shields. For an electric field, we can handle a Faraday cage which is capable to perfectly enclose our electronic. For a magnetic field, we have to deal with hyperpermeability materials, which are actually capable of conveying the lines of the magnetic field and shield our application from the effects of magnetic fields. How do we shield the radiation? The radiation can be shielded using different solutions. How do we measure the efficiency of this shield? Very easy, by measuring the ratio between the incoming energy and the transmitted energy. So we have an incoming radiation. A bit of this radiation will make its way through the shield. We measure the ratio between the two, taking care that some of this radiation will be reflected and some of these will be captured, will be still bouncing inside the shield as a secondary reflection. The ratio between the two, so the ratio between the transmitted energy and the incoming energy, can be measured, and we call shield efficiency, depending on the measurements of the electric field or the magnetic field, the number that we measure this way. Normally, for most application, an acceptable range of shielding is between 30 to 40 dBs. Please note that every 20 dBs, we have one order of magnitude. So every 20 dBs, we reduce our ratio by 10. 30 to 40 dBs are acceptable for, let me say, most of our applications. It means that more than 99% of the incoming energy is carefully shielded. For high-end or military applications, we will need higher dBs. And this is something that we are going to see in the next slides. How relevant is the thickness of the shield? You know, a shield is more effective as the thickness grows, but why and how? In order to understand the penetration depth of the electromagnetic wave, we have to understand which are the factors that are actually affecting this penetration depth. The penetration depth is a function of the radio frequency, of the material conductivity, and the magnetic permeability of the shielding itself. The relationship is described like this, and we can see that the depth, penetration depth of the radiation is higher for low frequency fields and for materials showing poor conductivity and poor magnetic permeability. And this is something that we have to keep in mind, because for high frequencies, maybe a thin sheet of metal can be enough, but for low frequency and for magnetic, especially for magnetic field, we will need something different. We will need a material which is capable of performing nice also at low thickness, so must be extremely conductive from an electrical point of view, and offering also some magnetic properties. And this is something that we are going to see in the next slides. Please keep in mind that polymers alone do not shield nothing, do not shield electric or magnetic field. We have to defend our applications from the incoming electromagnetic wave. How do we shield our application? We have two ways. We can reflect the incoming wave, or we can absorb it. What is better? Let's imagine we have this circuitry. We build a shield against it, all around it. Here is the incoming radiation. Some of it is reflected, but a bit of that can make its way through the shield. So it will enter and it will keep reflecting inside the shield. Never minding the fact that reflected radio waves can also affect other applications in the nearby. So reflecting electromagnetic waves is not a so desirable way to shield our applications. It is better to have a solution that can actually absorb it, especially when it comes to low frequency and magnetic fields. For this reason, we are now developing materials which are also capable of absorbing, not only reflecting, but also absorbing the magnetic field. If we have a solution that absorbs the magnetic field, both incoming from outside or generated from inside radiation will be easily conveyed on the shield and then grounded. And this is the best way, in our opinion, this is the best way to deal with electromagnetic shielding, no longer reflecting, but actually absorbing it. What are the traditional solutions when it comes to shielding? What are the best known solutions? You know this: metallic shields, so metallic enclosures, or overmolded metallic mesh. Very effective, but the weight of the shield can be a problem, especially when it comes to steel or copper, whose density is 5, 6, 7 times higher than that of plastics. Reflection, they can actually reflect. some of the incoming electromagnetic fields. Losses. Some of the incoming electromagnetic fields can make its way through seams better than through holes. So each time you're dealing with a steel cage, which is made out of metallic sheet, crimped together or whatever, you need gaskets, EMI shielding gaskets, and this can be a problem. Last but not least, don't forget that metals can actually be corroded by some specific environment. Another solution can be ESD powder or inks, but also in this case, process is not straightforward and is not easily scalable. The process and the application may not lead to really reliable solutions because you have to deal with the adhesion of this paint to the plastic part or metallic part. Cost can be quite challenging, and you may have also some problems from an environmental point of view. So you can see that already existing solutions are quite interesting, can be effective, but they have some issues concerning efficiency, concerning corrosion, concerning environment, cost, scalability, and also environment. What about our solutions? Plastic solutions. What is the advantage of plastic solutions? EMI shielding compounds, on the contrary, may guarantee a much higher design freedom because you can select the polymer depending on the boundary condition of your application, and you can then design the part satisfying all your requirements. Very flexible all-around application, all-around compounds can be tailor-made on demand, of course. The global warming potential of plastic solution can be smaller than that of metals, so also from an environmental point of view, plastics can be an advantage. There are no post-molding operations, so you need no painting, no despruing, no deflashing, no nothing. The part pop out of the mold, finished and perfectly shielding. Corrosion resistant, of course, because plastic do not suffer for corrosion. Molded parts have no seams, so also from a losses point of view, EMI shielding plastic parts can be extremely effective and with full potential. The process in itself, injection molding, is very straightforward, very easy and cheap, and reliable in time. Don't forget that conductive fillers are embedded in the plastic matrix, so actually they are protected by any kind of environmental issue. It's also very important to put the stress on the fact that EMI shielding compounds may also be designed not only to be EMI shielding, but also to provide other properties. By selecting the base polymer, you can have plastic parts that can actually withstand high temperature, right up to 200 degrees, 250 degrees. By selecting the right polymers, you may also have sustainable application, like those using post-industrial recyclates or post-consumer recyclates. And don't forget that we can tailor-make compounds for your requirements. Just to give you an idea, we can provide steel-filled compounds featuring carbon fiber, so structural and shielding for very demanding applications from a mechanical point of view. We can provide flame retardant shielding solutions and high temperature shielding solutions. Just go and check our website or drop a line out to our technicians to have a nice overview of our shielding materials. Now, the second part of this webinar is focusing on the performance that we measured with the University of Aachen on the already existing solutions and on new solutions, what we found out and what can also be useful for your very application. First of all, what kind of fillers did we test? Steel fibers, very conductive and efficient. Carbon fibers. Carbon fibers are well known in the words of plastic compounders, but we are never seeing them used as a shielding medium, EMI shielding medium. So we wanted to assess what is the performance of the carbon fiber. Graphite and carbon black. They both share their carbonious nature with carbon fibers, but they have different aspect ratio and different performance. Then we also worked with carbon nanotubes, multi-wall carbon nanotubes, very effective also with a very low content. And then we also tested some ferrites. What is the working mechanism of these fillers? It is called percolation. Percolation is a threshold between a non-conductive situation and a perfectly conductive situation. It means that from some value on of contact, you will between conductive fillers, you will have proper electrical conductivity. So percolation is achieved by carefully selecting the base polymer, especially the viscosity of the base polymer, the kind of filler, the type, morphology, and content, the right process. So you have to process them correctly in order to achieve a perfect dispersion without breaking, without destroying the fillers. The key word is networking. You have to be able to create a conductive network in your injection molded part. And the result is here. You can actually see how this percolation threshold will lead your application to a perfectly conductive solution, depending on the kind of filler. The testing method that we used was selected with the University of Aachen. Please note that there is plenty of methods to measure EMI shielding, but not all these methods are equivalent, and some of them are not suitable for some application or some material. The test that we used is the STM D493-599, which is called coaxial transmission line test method. This is the layout of the device. You have to put the material in between the two halves of this brass device, where you have the perfect flow of electric and magnetic field. It is suitable for flat specimen, so it is not suitable for complex parts as connectors. It is suitable for the far field, so for the behavior of the electromagnetic field far from the source. It is less accurate for the near field application. It worked perfect for a frequency between 30 MHz to 1.5 GHz, and it is also suitable for the so-called electrically thin specimen, meaning that the thickness of the specimen must be lower than 100 of a minimum wavelength of the incoming signal. We tested specimen 1.5 and 3 mm thick. As I told you before, the University of Aachen took care of all these measurements on our material. You can see the influence of the specimen thickness right here. That's the reason why we selected two different thicknesses. We were not satisfied by measuring only one thickness. We wanted to understand what happens changing the thickness to see if there is an improvement or if nothing happens. And you can see a first idea of the effect of the thickness right here. This is the stainless steel specimen, and you can see how moving from 1.5 to 3 mm, you can also gain one order of magnitude 20 dBs. This is the formula that was applied. First set of results. Stainless steel. How does stainless steel perform in shielding effectiveness? These are the results at 1.5 and these are the results at 3 mm, changing the stainless steel content from 5 to 10 to 15%. What do we see here? We see that the efficiency grows with thickness, going from maximum 70 to maximum 90 dBs. And we also see that the shielding effectiveness is influenced by the frequency of the incoming signal. We can also see the same results here in this other graph, where it is evident that for higher thicknesses, there is more or less no improvement by increasing the content of stainless steel, and noting that higher thicknesses are more efficient than lower thicknesses. This is something that we must keep in mind. If you want to use steel fibers as additive for electrically shielding compounds, you must always think to wall thickness as a critical factor for your device. So it's not only how much fiber you put inside, but also how thick your walls will be. The second set of results is describing the behavior of carbon fibers. We wanted to test 40% carbon fiber, high tenacity carbon fiber, and the results are very interesting. What can be seen here is that there is also in this case a slight improvement by increasing thickness, but it is not as evident as steel. And what is more important, these curves are more or less linear with frequency. This is also very interesting because this means that if we use carbon fiber for shielding purpose, the shielding efficiency will be less affected by frequency, and 40% carbon fiber can provide the same performance of 5% steel as an attenuation value. This is a very important result because normally we use carbon fibers for tribological application, for electrically conductive application, for structural application, but we never suggested carbon fiber for EMI shielding application. This graph here shows that carbon fibers can provide very nice performance also from a shielding point of view, and it is evident that dependency of the shielding efficiency with frequency is not as complicated as steel fibers. This is also very important because we are going to see in the next slides that this result suggested us another experiment. As you can see, this is also a comparison carbon fiber with steel fibers. 40% carbon and 5% steel perform more or less the same from a shielding efficiency point of view. Now let's jump into the next experiment. What happens if we mix steel fibers with carbon fibers? So we make a compound which is actually featuring steel fibers and carbon fibers at the same time. What we found is that the result is very interesting because you have a very, very high shielding efficiency, but you have a much lower effect of thickness and frequency. And in our humble opinion, this is a very important result that deserves further investigation, because the efficiency was very high even at low thickness, at 1.5 millimeter, and was less influenced by frequency. Why? We try to understand why did this happen, because the performance of this compound was much better than the sum of the performance of only steel or only carbon. Is there a synergy between steel and carbon fiber? On this graph, you can see the performance of the mixture, steel and carbon, which is the continuous blue and orange line, versus only steel, which is the dotted line. You can see that mixing a bit of carbon fiber with steel fiber will vastly improve the overall performance from a shielding point of view, but will also affect the shape of the curve, flattening it somehow. What is the reason of this? We thought that the main reason is due to the orientation of the carbon fiber, especially in the low thickness. In this graph here, you can actually see how the 1.5 millimeter thick mixture steel and carbon performed better than 3 millimeter of only steel. We think that orientation improves networking, improves the grade of the number of contact between conductive particles, and both shielding efficiency and shield response benefit quite a lot by adding carbon to steel. That's the reason why we are now developing a full range of compounds, which is actually featuring various concentration of steel and carbon fiber to propose a new family of EMI shielding properties. What is the other benefit of this application? With only steel, you will not have any mechanical improvement of your device. By mixing carbon and steel, you improve the shielding efficiency, but you will also improve the mechanical property of your application. And this can be a huge advantage for many situations. Fourth experiment, graphite. What happens with graphite? Very poor shielding. I must say that this graphite is suitable for thermally conductive applications. We used LATICONTER, which is a thermally conductive compound, so maybe it is not the best graphite for EMI shielding, but we saw a very slight improvement, very low shielding efficiency. For sure, the filler shape, orientation, and dispersion was not optimal. We also wanted to test the same experiment. What happens by mixing graphite and steel fibers? Actually, there was no improvement. By mixing also a huge quantity of graphite to steel fibers, we saw no benefits in the shielding efficiency. Maybe we were not able to create a properly developed networking of graphite particles. Maybe we should change the type of graphite or change the shape or increase the content, but we didn't see this synergy between graphite and steel fibers. The same issues were detected with carbon black and carbon nanotubes. Carbon black particle quantities aspect ratio is very important. It's very important to improve filler dispersion. The measurements we saw from a shielding efficiency point of view were very similar to graphite, so were not actually acceptable, less than 15 dBs, which is really quite small. For carbon nanotubes, we saw almost no benefits. But this was a problem of, in my opinion, this was a poor problem of dispersion, because it's plenty of literature showing how carbon nanotubes and graphene can actually offer a very interesting, very acceptable shielding efficiency. The last results were developed on ferrite. We tested the so-called MDT17, which are magnetically detectable ferrites, and in this case it didn't work. And also hard ferrite, which is the strontium ferrite, which actually provided acceptable results. But we think there is a lot of improvement to be done with ferrites, especially when it comes to magnetically field absorbing shielding applications. And we want also to test what happens by mixing ferrites with steel fibers in order to have a compound which is actually providing a very good magnetically shielding and electrically field shielding performance. Now, some conclusions. We put on this graph the shielding effectiveness at 1.5 millimeter of all the compounds that we tested. The results are evident. The steel and carbon mixture performed much better than all the other. So we had the maximum shielding efficiency at the lowest thickness using the stainless steel plus carbon fiber compound. The pure steel fibers provided a nice efficient system, but we already know that, which is actually quite depending on the amount of steel fibers and shield thickness. Carbon black, carbon nanotubes, and ferrite did not provide any, let me say, any exciting result. The mixture of graphite and stainless steel did not show any synergy, so this was more or less not a success, I would say. And graphite alone did not offer any shielding properties. Why is it important to keep developing this graphite and stainless steel solution? Because graphite is providing thermal conductivity. So if LATI is able to develop a perfectly EMI shielding and thermally conductive compound by maybe adding some carbon fiber to graphite and steel fiber, you can have a thermally conductive, heat dissipating solution, which is also EMI shielding. That's the reason why we will keep working in this direction. Same results, 3 millimeter. You can see that the carbon steel compound is no longer affected by the thickness of the wall. On the contrary of this only stainless steel, which is boosting its performance at higher steel content and higher wall thickness. And the mixture of carbon black, carbon nanotubes, and ferrite did not show any evident difference, also increasing the wall thickness. The comparison between 1.5 and 3 millimeter thick specimen is confirming what I told you before. So we saw there is a very interesting and worth developing synergy between steel and carbon fibers. So we have to develop new compounds, changing the ratio between steel and carbon to find an optimal answer. Steel and carbon filled materials featuring both filler at the same time perform very good, also very low thickness. Steel fibers are very affected by the wall thickness. With 3 millimeter thick specimen, 10% and 50% steel fiber did not perform that far. Carbon black and carbon nanotubes did not show any effect, but actually I think this is a problem of dispersion and aspect ratio. Last slide of my presentation. Carbon fibers show a very good shielding efficiency acceptable for most applications, up to 40, 50 dBs, which is very nice because it is more or less the numbers of 5% steel. And carbon fiber is already effective at very low thickness. Graphite did not show very efficient behavior or synergy with steel. For sure, we have to improve the dispersion. We have to change the aspect ratio of the flakes, and we also have to study what happens adding some carbon fibers and steel to graphite. So I really hope I was able to give you a decent overview of this experiment. This was an experiment that took 1 year actually to develop. I really hope I was able to give you a decent overview of these results. I really hope that you will now have some inputs for your applications. I'm here open now to answer your questions if any. So I see a few questions right now, a few questions popping up. The first question is: have you got already available grades featuring carbon and stainless steel? Yes, we have. I told also along the way that we have this 50% steel with carbon fiber was one of the first products that we developed. Now we have at least another 4 or 5 different grades. We are working with PPS, we are working with nylon, with aromatic polyamide, changing the ratio between carbon and steel in order to find the best mixture, because it is not straightforward to injection mold steel fibers. So it would be a great success if we could find that maybe 5 to 7% steel is already capable with 15 or 20% carbon to provide a very all-around effective solution. Yes, so anyhow, get in touch with our salespeople or with technicians, and we will be happy to answer your questions. The second question is concerning mechanical improvement of stainless steel. No, stainless steel do not provide any mechanical improvement of mechanical performance. Stainless steel are very soft, and please note that we add up to 10-15% content, which is a very low fraction when it comes to volume. Stainless steel used in electrically conductive plastics is very soft, is not capable of any mechanical improvement. If you want to improve the mechanical performance and still have an EMI shielding performance, you can rely on carbon fibers or glass fibers. Yes, this is the best way. Please remember that injection molding, correctly injection molding steel fibers is not easy, because you can easily clog your nozzle. You can easily break them during the injection molding phase. So This is also one of the reasons why we are trying to develop the carbon steel hybrid for the next soon to come applications. The third question is if we have shielding data at high frequency. High frequency, I think, means 40 to 70 gigahertz, which are the frequencies used in modern equipment. No, we haven't yet. I wish we had actually, but we were not able to find the right partner to develop any of these measurements. Yeah, if you have any contacts, or if you are capable of doing this shield, it would be really very nice, very nice to have some relationship. Maybe we can provide some specimen. Then we have another four questions. A lot of questions popping up right now. So why did you choose stainless steel and not something more conductive like copper or aluminum? Very interesting question. We found on the market, we found stainless steel fibers, and we compounded stainless steel fibers because it is easier to create the conductive network. We also tested copper, aluminum, and brass and bronze powders. But with powders, we didn't make any measurements because resistivity measurements did not show an exciting performance. But I think your question is very interesting because working with these hybrids with fibers and powders, this could be a next experiment to be done. We are planning a new set of experiments for this winter, and it would be really very interesting also to find out what happens with copper powders. We refrain from aluminum because it's actually creating a mess in our equipment, but copper is already used, and it would be very interesting. Have you checked if injection point location has an impact on performance? No, actually we didn't, because we were supposed to injection mold plates, and plates are injected on the side with a large fan gate, creating a more or less high orientation, uniform orientation. But your question is very interesting, because injection location can affect quite a lot fiber orientation and networking. So also in this case, it would be interesting to measure if something changes. The point is that by injecting plates, we have only this tool, which is injecting plates. So we were not able to measure if injection location is making the difference. But for sure it is. For sure it is, because it will affect fiber orientation. Another question: can we mix such shields with eco materials as Lecolati? For sure you can. For sure you can. We can, as I've shown in my presentation, you can mix EMI shielding fillers, never minding the base resin. You can use sustainable base resin from post-industrial or post-consumer plastics. Yeah, we have recycled polycarbonate, we have recycled polyamides. We are dealing with some recycled polypropylene. Yes, so the question is definitely yes, you can. Fourth question: thank you for your very nice presentation. Have you tried with non-magnetic steel? This stainless steel that we are using has a very low magnetic performance. But to answer your question, if we had to try with fully, let me say, non-magnetic steel, I think we would have a nice shielding from electric field, but the performance on the near field and magnetic field could be somehow questionable. That's also the reason why I'm looking forward a new set of experiments mixing non-magnetic steel with some ferrite. This is one of my, let me say, of the worms I have still in my ideas. I would like to see what happens. This is one of the incoming set of experiments anyhow. Do you have PA-based compounds UV resistant, antistatic, and with good impact resistant? So PA-based compound, UV antistatic, and good impact resistant. Yes, we have. Anyhow, please note that antistatic or conductive means filling up quite a lot your material with conductive filler. Impact resistance means most of the time adding some elastomer, and this solution goes on the opposite of antistatic. So it is easier to have a fully conductive impact resistant, maybe mixing some rubber, some elastomer with stainless steel. You can have the solution. Just to give you an idea, we have some rubbers with steel fibers inside, which are perfectly impact resistant and conductive. But if you need antistatic, so it means the conductivity 10 power 9, 10 power 10, it may be a bit more difficult. Just get in touch with your Lati sales guy, and we will try to manage to source something out. Shielding efficiency is directly proportional to surface resistivity. Somehow we can relate it, because the more conductive the material is, the more effective will be in order to create a Faraday cage. But as I explained in this webinar, this may not be enough. This can be enough from some frequencies and some shape, let me say, of the electromagnetic radiation, but it could be less effective when it comes to near field and magnetic field and low frequencies. For low frequencies below 100 kilohertz, it could not be an interesting value. It could not be enough. So I think we have finished our time. I really thank you for your questions. Very interesting. I'm really happy to find that my webinar was interesting. Please give a look at all other Lati webinars already done in the past. You can find them on our LinkedIn or YouTube webpage. I will be happy to answer all other questions that you may have. You see here my personal email address. Drop me a line or get in touch with Lati. I thank you so much for your attention, and I'm looking forward to meeting you in the forthcoming webinars. Thank you and have a great day.